Alright, so now we're going to look at the last part of our derivation, proving why planetary orbits are elliptical by linking everything we have done so far. So in the previous part we have established this circle, whereby we have which represents the shape shape that the velocity vectors draw from this point over here. So the velocity vectors trace something that looks like this. They're all equal angles apart from each other. Not equal angles, they're all the changes, the delta v vector, they were all same. So it's just like drawing a polygon, but then having all of them linked to a point that is not the center. This is the center, and the point that they all link to they all bind to is not actually the center. So we could say it will look something like this, whereby we have a polygon. Imagine a polygon. It's going to go here and then here and then here. So these will be the collection of the vectors we have. The velocity vectors from this diagram over here, where we had divided this orbit into parts with equal angles. Something that looks like this. Now if we draw a few more lines, we get, for clarity, we're gonna get something like this. And now, keep in mind that the velocity vectors here are basically from this diagram over here. So this is the velocity shape, and this is the orbit. And the velocities are basically all of them from here, and we have just basically gathered these points all together to one point, and then we're seeing how it looks, and we established that it will form something close to a circle. When we had infinitely many regions, so d theta, we divide by each region by d theta, we're going to get a perfect circle. But we're not going to do that because we don't have to. Okay, so we get something like this. And of course, this here is going to be getting smaller until here it's going to be the minimum, and there it's going to be the maximum. Well, now, how do we link these two together? And we're going to focus on only one velocity vector. And in this case, we're going to look at, do we have the right number? 1, 2, 3, 4, 5, 6, 7, 8. Okay, we're just going to focus on this one over here. So let's call this here theta. This angle that forms this vector over here, we're going to set that as theta. And then what we're going to do, well, first of all, we know that we know that this here will correspond to, I didn't draw 16 lines here, but if I draw 16 lines here again, because the number of vectors must match, because they're basically the same diagrams. We're getting these vectors and depicting them by setting these starting points in one point. So we have, if you draw, imagine 16, and have if you have something like that, we're gonna have this, that, and that. So here and here. And here, here. So that would be our 16 vectors. And so what would correspond to this vector over here? Well, this vector over here is going to be the third, when you imagine it's going to be the third largest vector in terms of magnitude, and will be pointing to the left. And so it will correspond to first, second, third, this vector over here. Let's say I'll label it V, like that. So how do we find the relationship between the two? First of all, what I'm going to do is I'm going to rotate this clockwise 90 degrees, firstly. And I know that we have to switch, because I have rotated 90 degrees, to make it equal to this vector again, I have to rotate it anti-clockwise 90 degrees. But still, for the sake of to solve this, we're gonna imagine rotating this diagram 90 degrees first. And then you'll see how I will rotate it back anti-clockwise 90 degrees later. But for now, I'm just gonna rotate this diagram 90 degrees, which will give us the following diagram. So we had the focus, we had the center here and the focus here. And so now we are gonna have the focus over here, because we are rotating 90 degrees. And imagine the circle being like that. And we basically have the same shape. We have these arrows. Now I'm gonna have to be precise quite. So that's our new diagram, whereby we have rotated the same diagram 90 degrees clockwise. And now, we have seen this shape before over here. We have the center of the circle, and we have one focus. Now keep in mind that we were looking at the third largest vector. So before it was, when we imagine this way, it was this here. So we're looking at this one over here, this vector. And what would correspond to this theta over here? Well, now we know that because the acceleration of, because you know the change in velocity, we could represent that as the acceleration. We know that the change in acceleration, so the effect of acceleration would be same either in this diagram over here and this diagram over here. And so this would mean that if we have the center over here, you could say that if we plot a line like that from this line, from this the center here to this point over here, let's call that P, we could say that this is equal to theta, as that is equal to theta. And now we are used to looking at this shape before. What did we use? What did we do with this shape over here in the first part of the video? Well, we from this shape we were able to draw an ellipse by looking at the relationships between the lines over here. And so first of all, we looked at, well, now I'm gonna use a different color pen. First of all, we looked at, well, the midpoint between, I see this is C of F, that's C. Between F and P, it's going to be somewhere over here. And we looked at the perpendicular bisector. Alright, this is a perpendicular. And then we looked at, well, we have this line, and because this is a right angle and these have the same lengths, we can draw this line and say that, well, these two are equal. And now, what's important is about this line. What would this line be equal to? We know that before we had something like that. We had a line that's parallel to this vector over here that looked like that. And then we have rotated 90 degrees. And so it now looks like here, this vector over here from F to P, this over here. We have got something that looks like that. And now what we're doing is we're rotating it 90 degrees back anti-clockwise. Well, it doesn't really matter clockwise or anti-clockwise because it's 90 degrees, but you get what I'm doing. We have rotated 90 clockwise. We have rotated this vector, this whole shape 90 degrees, and so this vector too. And then we're rotating it back anti-clockwise 90 degrees, and so we get the same vector we started with over here. This vector. And what do we know about this shape? Well, from here we know that, well, first of all, this is C. Line CP is radius, so line CP is equal to the radius. And then we also know that when I say that's Q, this point here, due to the congruency of the triangles PKQ and FKQ, due to congruency, FKQ congruency, PKQ, we get PQ is equal to FQ. And we know that this line CP here is composed of CQ plus QP. And now we said that QP or PQ is equal to FQ, so this is equal to CQ plus FQ, which means that CQ over here, which is this line, and CQ over here, which is this line, and FQ, which is this line, they are equal to the radius R over here. And you know that we all know that the radius from C to P, C to any P, well, this could be P2, this could be P2, this could be P, anything could be P. And we know that the line CPU is the radius, which does not change in a perfect circle. Which means that, and we also know that this here we have established in the first part, that it is tangent to the eclipse that we could draw from this principle that the sum of FQ plus CQ, whereby Q could be any point determined by any P, we know that their sum now is a constant value, and that this line over here, which is the velocity vector we started with, this over here, velocity vector, that is tangent to our ellipse over here, and we could draw like that. And so this basically proves why planetary orbits are indeed elliptical, because all of these velocities are tangent to an ellipse that we could draw, an ellipse that we could draw. It means that basically planetary orbits, because the velocities of objects that travel around a set focus by planetary motion, because their motion tangential to the orbit is in the form of an ellipse, we could therefore state that planetary orbits are indeed elliptical. And the proof why this is actually tangent to this line, this vector over here is tangent to the ellipse. We could prove this by imagining well, we had CP, right, like that. Well, imagine CP. Well, CP could be, or Q. Let's imagine Q. Q could be any point along this tangential line, this perpendicular bisector, and it will give something. If it deviates from, this original point over here, the more it deviates, the more the value increases. Either away from this point where it gives a straight line, like either left or right, it will give a value higher. And because we know that, therefore, this straight line, we know that, and like the shortest path between 2 points is going to be a straight line that links both of them together. And so because the shortest path that links between C and P is a straight line, we know that all of these do not give us just an increase from that length that gives us a straight line, which means that this perpendicular bisector over here is indeed the tangent line, because all of these just give an increase. And so that's how Feynman proved in his last lecture, and the name last lecture is given because this lecture, the recording, or what he said in this lecture about how he proved elliptical orbits, it was lost, and that's why it's called the last lecture. But anyways, this is how Feynman proved why and how planetary orbits are not in circles but in ellipses in his last lecture. So that's the proof. I hope you enjoyed it. Please like and subscribe if you want to give. Please like and subscribe, and leave a comment down below if you want to give any suggestions to the channel. Thank you, and I'll be back with a video. The next video is I think it's gonna be about taking a calculus method, a differential method, using the Euler-Lagrange, not the Euler-Lagrange, using some complex calculus to do the same thing, proving why planetary orbits are elliptical. This method over here, Feynman's method, it was kind of an intuitive approach that didn't really require any understanding of complex calculus. But in the next video, I'm gonna be taking a calculus method in proving why planetary orbits are elliptical. So thank you. That was my video.